Despite the fact that the SI unit for pressure is Pascal, chemists all around the world continue to use different units for pressure because they're just accustomed to it. So the Pascal is the SI unit for pressure, but most of the time you'll see in your books and in different types of research journals from chemists and scientists, they instead like to use atmospheres, torrs, or millimeters of mercury. Sometimes you might see bars as well. So the Pascal is the SI unit, but they tend to like to use these other types of units for pressure. Now, here we have the different names for pressure. All of these are just different types of pressure, basically different units for it. They're all saying the same thing. An atmosphere is a unit of pressure just like a torr is, just like a bar is, just like a kilopascal is. It's going to be important that you guys know how to convert from one to the other. It's a long list, but the ones that professors usually focus on the most are atmospheres, millimeters of mercury, torrs, and bars. Those are usually the ones that we see the most. And of course, pascals. And just realize, all of them are equal to one another. So we can say that 760 torrs are equal to 1.01325 bars. You could say that 1 atmosphere is equal to this many pascals. All these units are in agreement with one another. They all equal one another. We're going to say that 1 atmosphere equals 760 millimeters of mercury, or 760 torrs. What I also want you to see is that, just look at these two right here, the millimeters of mercuries and the torrs. They both have the same number. So 760 millimeters of mercury equals 760 torrs. What this really means is that for every 1 millimeter, what this means is for every 1 millimeter of mercury, we have 1 torr. They're basically the same units. So just remember that what the SI units for pressure are, what are the SI units for force, what is pressure defined as, and then the connections between the different units for pressure. Because when it comes to gases, we have to remember this, because pressure plays a very large role in the property that a gas has.
Gas. It's all around you. It's in space. It's on Mars. It's dissolved in your blood and in your soda. It's everywhere. And it's easy to forget that we're submerged in an ocean of gas, but it's there all the time. You can feel it if you wave your arms around. You can't look cool while you're feeling it, but you can feel it. It's there, those little molecules and atoms bumping around against your hand as you wave them around. Feel it? Are you doing this? I've got good news and bad news about gases. First, the good news: when they're behaving themselves, it is extremely easy to describe their behavior theoretically, experimentally, and mathematically. The bad news is they almost never behave themselves. The first mathematical description of the behavior of a gas was a link between pressure and volume. In a closed system, like the inside of this balloon, when we decrease the volume of the balloon, the pressure inside goes up. And if we could somehow expand the balloon, then the pressure inside the balloon would go down. If I keep pushing on it, the pressure inside might go so high that it'll break. I can't do it. It's a very strong balloon. The relationship here is a simple one. When you multiply the pressure and the volume together, you get a constant. As long as the temperature and the amount of gas stays the same, so does that constant. It's called Boyle's Law, and it was a pretty big deal back in the 1600s. It's also one of the greatest scientific misattributions of all time. Henry Power's Wikipedia page didn't even mention Boyle's Law until a few weeks ago, when I personally added a paragraph about it, with proper citations, of course. But no matter who thought it up or who it got named after, Boyle's Law is pretty cool. For a given amount of gas at a constant temperature, pressure times volume always equals the same number. But where is that constant coming from, and why is it different for different amounts of gas at different temperatures? Well, it was more than 100 years before we'd figure out the answers to those questions with the help of a Frenchman, Jacques Charles, and our old Italian house elf friend Amedeo Avogadro. Charles and Avogadro created equations much like Boyle's Law, with two features of a gas being linked directly together by constants. Charles discovered that volume divided by temperature equals a constant, as long as the pressure remains the same, and then Avogadro figured out that volume divided by the number of moles in the container at a constant pressure and temperature gave yet another constant. But here's the crazy cool cool thing, all of these scientists were basically dealing with a different form of the same equation. An equation that we must never forget, and is going to be stuck in my head until I die. And here's how it works. Pressure times volume is equal to the number of moles of substance times a constant times temperature. PV equals nRT, the ideal gas law, which works for all gases as long as they behave themselves. Now here's the cool part. Using this equation, we can show how all of these chemists were dealing with the same relationship. They were just clumping various variables together in different orders. All of the chemists we just mentioned, Charles, Avogadro, and Boyle, or more properly Townley and Power, figured out their contribution to the ideal gas law experimentally. But more interesting to me is that it can be understood theoretically. First, we have to understand what each of these variables actually mean. In that same way, the atoms and molecules that make up gases are bouncing against things, applying pressure to them. This balloon is inflated because the molecules are bouncing around inside of it, bumping into the inside of the balloon harder than the molecules bouncing off the outside of the balloon. Scientists generally measure pressure with the SI units of force, newtons per area, meters squared, which is shortened to pascals. But since pascals are so tiny, we either use kilopascals or we use the pressure here on Earth at sea level that we call 1 atmosphere or 1 ATM. Completely by chance, 1 atmosphere is equal to 101,325 pascals, but that's so close that we often just say that 1 atmosphere is 100,000 pascals or 100 kilopascals. Volume is the amount of space particles have to exist inside of, so yeah, that makes sense. When the volume goes down, the pressure goes up because there are more particles in a smaller space and they'll each hit the walls more often. And is simply the amount of gas, the number of moles in the system. Here I am decreasing the amount of gas in the system, and in response the volume is decreasing, obviously, but so is the pressure inside the balloon. R in the ideal gas law is called the universal gas constant, even though, as we will see in a coming episode, it is neither universal nor constant. It's 8.3145 liter kilopascal per Kelvin mole. Temperature is experienced by you and me as hot or cold, but at the atomic level it's kinetic energy, literally how fast or slow the average particle is moving. So if temperature goes up, so will the pressure, as the particles are moving faster, and thus will run into the sides of the container more often.
Hi, this is Dr. McCord. I'm going to talk to you today about Dalton's law of partial pressures. We're going to start out with the ideal gas law, which is PV equals nRT. We're also going to solve for P here and just get it written in terms of the number of moles, the temperature, and the volume. We're also going to hold the temperature and volume constant so that we can split out the RT over V term. We're going to call that a constant, and this really allows us to kind of think about pressure only in terms of the number of moles. What that means is pressure is directly proportional to the number of moles. So it's real easy to think about the calculations here. So if you double the moles, you double the pressure. You triple the moles, you triple the pressure. You get the idea. So we're going to first start with a container here. If you need to know what the container size is and the temperature, we'll go ahead and give you that. 244.7 liters at 25 degrees C. Now we're going to put 1 mole into this container, and we get 0.1 atmospheres of pressure. We're going to then double this up to 2 moles, and we're going to get 0.2 atmospheres of pressure. And as you can guess, if we go to 3 moles, we get 0.3 atmospheres of pressure. And this becomes really easy to just keep going, count 4 moles, 5 moles, go all the way to 6 moles, you'll get 0.6 atmospheres of pressure. You go to 7, you'll get 0.7. And we'll take this all the way up to 8 just to make a point. But we really want to shift our focus now into several containers combining to make a mixture. So let's imagine we have 3 containers like this and explore Dalton's law of partial pressures. So here's 3 containers. We're going to label them A, B, and C for the gases that we're going to put in them. We're going to put 10 moles of gas A. We're going to put in 6 moles of gas B and 4 moles of gas C. That's going to give us 1 atmosphere for A, 0.6 atmospheres for B, and 0.4 atmospheres for C. We're also going to quit counting in moles. We don't need moles to do Dalton's law, so we're going to just think about it in terms of pressures. And now we're going to combine these amounts and make a mixture. So we're going to take each of these three containers and now push all those moles together into one container. It's easy to do the math. We now have 20 total moles in the container, and it turns out that the pressures add up in the same exact way, and we get 2.0 atmospheres of pressure in the container. So to summarize, we've got 20 moles total. We've got 2 atmospheres of pressure. Now you need to remember the ideal gas law does not care what kind of gases you have. So 20 moles gives you 20 atmospheres. Now I'm splitting things back out on the right to show you the separate containers, and I'm also showing you the mixture. I'm going to put a dividing line here to show you that there's the two different ways we think. On the left is what the mixture holds. We just count number of moles. We don't care what they are. But on the right is more of the way a chemist sees things when he's looking at a mixture. We really see it as the 3 separate partial pressures that combine to give the total pressures. That's exactly what Dalton's law is all about. So the way I see this is partial pressure of A, the partial pressure of B, and the partial pressure of C all combine to give the overall total pressure in the mixture. If I take all those quantities and make a mathematical relationship out of them, I have the very definition of Dalton's law of partial pressures. We can also state this law in words. Dalton's law simply says that the total pressure of a mixture of gases is equal to the sum of the partial pressures. It's a very handy law, and it works for as many gases as you have in a mixture as you want. This has been Dr. Paul McCord talking to you about Dalton's law of partial pressures. Have a good day.
Hey guys, it's Miss Stites here, and we are going to be doing a gas stoichiometry lab. In this lab, we're going to take magnesium metal and react that with hydrochloric acid. And we're going to do this reaction in a special device that's used to capture and measure gas produced from a lab that is known as a eudiometer. And this is what a eudiometer looks like. It is just a glass tube that is graduated similar to a graduated cylinder that's measured in milliliters, and that is going to help us figure out how much gas is produced from this reaction. So what I've done is I've taken 2 centimeters of magnesium and 5 milliliters of hydrochloric acid, and we're going to combine those 2 reactants. And what we should expect to form from this experiment, since this is going to be a single replacement and magnesium is capable of replacing the hydrogen and hydrochloric acid, we should expect magnesium chloride to form, and then of course the hydrogen gas, which is what we're studying in this unit. From this equation, we can see that for every 1 mole of magnesium, it's going to require 2 moles of hydrogen chloride in order to produce our magnesium chloride and hydrogen gas. So let's get to the experiment. Like I said, I've taken this 2 centimeter strip of magnesium metal and I placed that on the balance and found out that this magnesium metal weighs 0.02 grams. And then I'm going to be using 5 milliliters of hydrochloric acid. So these are my 2 reactant amounts. I have already added the hydrochloric acid to the eudiometer up to the 5 milliliter mark. And I have taken that magnesium ribbon here and I have coiled it and then attached it to a piece of string. So my next step, since I have my magnesium metal weighed and tied to my thread, and my hydrochloric acid I've already poured into the eudiometer, the next thing that I need to add is distilled water to my eudiometer tube. So what I'm going to do is I'm going to tilt this sideways so that when I add my distilled water to the tube, the acid and the distilled water do not mix quite yet. So if I do this and try to record it at the same time, I'm going to fill this eudiometer tube all the way to the top. Mixing, and Miss Grody is here to save me and help record. There we go. Alright. Adding this all the way to the top with distilled water. I can allow this to hang straight now. All the way past the graduated, we want no air left inside the eudiometer tube. I'm going to take my magnesium that I've tied to my thread, and I'm going to add that to my eudiometer tube. Allow that to sink in. I'm going to keep some of the thread out, dangling off to the side. With my rubber stopper that has a hole in it, you never want to completely cap something that's going to produce a gas, because pressure will build and things will explode, and that's not what we want to happen. So I'm going to stopper that. And then I'm going to invert this eudiometer into my trough of water while I keep my thumb over the stopper. Once the eudiometer is in the water, I can remove my thumb, and then I'm going to attach it back to my clamps so that I don't have to hold it. And what's happening right now is, because the acid and the water are different densities, they are starting to mix. So the acid that was originally in the bottom of the eudiometer, which is now at the top, is sinking and mixing with the distilled water that we added. So you can see the swirling as the acid reaches the magnesium metal. Now we're seeing the reaction begin. And this is known as collecting gas over water. So what's happening, the bubbles are traveling to the top, and soon they're going to start to replace the water and push it out of the eudiometer tube. And when the reaction stops, we'll be able to tell from the eudiometer tube how much gas we've collected. So we have to wait until all of the bubbles stop. Starts slow at first, but now it's picking up. And you can see the metal has completely changed forms. And from our chemical equation that we wrote, we can see that we've got magnesium chloride mixing in with the water, and then the hydrogen gas that's produced. So the magnesium hasn't just magically disappeared, it's just changed forms from the reaction. It appears, we're going to wait for these bubbles to settle, and then I'll show you how to remove the tube. I think that is all we're going to get. In order to get an accurate measurement, we have to put this eudiometer into what's known as a leveling tube. Well, we're going to use this large beaker here in order to do that. We want to make sure that the water level that's in the tube is equal to the water level in the beaker, so that the pressures are even, so we can get an accurate measurement of how much gas has actually been collected. So I need to place my finger over the hole so that none of this liquid inside the UDometer comes out. In this next step, we are going to take the UDometer and we're going to put it into the sink. And this is going to be a leveling device. So basically what we're doing here is we're going to line up the level of liquid inside the UDometer with the same level of the water in the sink. And what this is supposed to do is just to make sure that the pressure inside and outside of the tube are equal. This is just an easy way of figuring out the pressure inside the tube. So we're just going to use barometric pressure, which today is 30.16 inches of mercury. So once I have that level, I'm going to put my finger back over the hole in the stopper and lift this out. And I can see that we have collected 34.6 milliliters of hydrogen gas. What we need to do is then just record the temperature of the water, and this is at 19 degrees Celsius. So we have our completed experiment now. Our numbers, once again, the air pressure is 30.16 inches of mercury today, so we're more than likely going to need to convert that into millimeters of mercury. The temperature of our water is 19 degrees Celsius. The mass of the magnesium we used was 0.02 grams.
The kinetic molecular theory is the theory that all matter is made up of atoms and molecules that are always moving. These particles hold kinetic energy and move around in random directions. In higher temperatures, the particles have high energy, and in low temperatures, the particles have less energy. The more energy a particle has, the faster it will move. In solids such as ice, the particles hardly move at all and hold a regular pattern because the energy is low and the particles are tightly packed. In liquids such as water, the particles have more energy and the freedom to move around. Liquids have the ability to flow and fill the shape of any container they are put in. In gases like steam, the particles have the most energy. These particles are sparse and move around freely. Gases are usually invisible to the eye and they can be expanded and compressed in different pressures. All matter is composed of atoms and molecules that are always moving. The higher the temperature, the more energy these particles have, and that is the kinetic molecular theory.
What is going on, guys? It's Bucky and welcome to your 9th chemistry tutorial. And in this tutorial, I'm going to be talking to you guys about something called the quantum mechanical model. Man, that just sounds fun already. So anyways, what chemists did was, once they started looking at really complex atoms, they tried to take the model that Bohr came up with and they tried to apply it to these really complex atoms, and they found out that it didn't really fit. It didn't really make sense. So instead, they said, okay, Bohr, your model's good for the more simple atoms and elements, but for this complex stuff, we need a complex equation. Hence, the quantum mechanical model. Let's go ahead and dive right into it. So basically, what the quantum mechanical model is it's this formula, I guess you could say, pretty much a way that chemists can predict how electrons spin around the nucleus. They figured out that it's instead of simple circular orbits like Bohr said, they actually spin around the nucleus in this very complex 3D paths, and you really need a bunch of different numbers other than, orbit number 1, orbit number 2. You really need a bunch of different variables in order to figure out just exactly and calculate the path that those electrons take. So those numbers are n, which stands for the orbital's energy, L, which stands for the orbital shape, ml, which is the orientation or how it's tilted, ms, which pretty much means is your electron spinning clockwise or counterclockwise. And with those four numbers, you can go ahead and calculate a formula to figure out a really complex 3D path. And this isn't like any random, this is actually one of the paths that electrons take. I just didn't make a weird 3D model and plug it in here. This is actually one of the quantum mechanical models. So this is the path that electrons take. Pretty weird, huh? A lot more complex than a simple circle. So let me go ahead and break apart these numbers, and once I break everything apart and put it back together, you're going to see how you can use these four variables to calculate the exact path that electrons take. Let's go ahead and touch on the first one, which is orbitals energy, or other words, n is the variable that they used. Now technically this n is called the principal quantum number. I just say orbital's energy because it just makes sense. It basically is the orbital's energy. They just had to put a scientific term on it. So what this means is it's pretty much the average distance of the orbital from the nucleus, or in other words, the average distance that the electron is from the nucleus. And it can be any whole number, 1, 2, 3, 4, exactly like Bohr's orbitals. You know how Bohr's orbitals were labeled 1, 2, 3, 4, and so on? It's the exact same thing with this n. And of course, the larger the number, the bigger the orbital is going to be, hence further away from the nucleus. So 1 orbital is really close to the nucleus, and 4 is really far away from the nucleus. So now that we understand n, let's go ahead and talk about L, the orbital's shape. So technically this one is called angular momentum quantum number, but I'm just going to go ahead and say L equals orbital's shape. So basically the value you can have for L is n minus 1. So say for example that your n value, let me just pick one, say your n was 4. Well, according to this equation, it can be n minus 1, so 4 minus 1 is 3. So L can be equal to 0, 1, 2, or 3. So that's what I mean. L equals n minus 1. Whatever your n is, take 1 away from it, and that's what values L can be. And you're saying, okay, how can one number represent a shape? That doesn't make sense to me. Well, basically what they did was they paired up a number with, and they just made them represent different shapes. For example, whenever you have 0, it represents kind of a sphere shape. Whenever you have 1, it kind of looks like two balloons are pressed together, and we'll look at the shapes later on. And this is a really complex one. Let's see, where is it? Right there. This is a really complex one. That isn't 0 or 1. It's one of the higher ones. I can't even remember just by looking at them. I need the graph with me. But anyways, that's what you come up with if you go deep enough. It's like Inception. So anyways, the different numbers just represent different shapes. So just remember right now that n equals the size of the orbital and L equals the shape of the orbital. Two numbers we learned so far. So already we came into kind of a problem. Whenever you're writing these numbers together, it's kind of confusing because you try to write them together and it doesn't really look easy. I mean, you can say, okay, 1 equals n, so 0 equals L, so I'm going to write 1, 0. Now that looks like a 10, and no, these all kind of look like 10. So how can I take two numbers, be able to write them together without getting it confused with a number like 10 or 32 or 21 or something like that? So what scientists decided to do is, instead of keeping the number for L, they decided to give the L value a designated letter for each number. So whenever you have 0 for L, you write S instead. Whenever you have 1, you write P. So that way, instead of something like 1, 0, which may be confused with 10, you write 1S. So that solved the problem of having to write two numbers together. And if you write two numbers together, it just turns into a bigger number. So this right here solved that problem. So again, to sum up this entire tutorial, remember this. There are four numbers that you need to calculate the path of an electron. We learned two of them already. N, which is this first one, is the size of the orbital, and the second one, which is the L, is the shape of the orbital. So this 1s right here means the orbital is pretty small, and the S, is a sphere, and we'll look at the shapes later. So this 1s is a small spherical shape. So we still got 2 more variables to cover, and in the next tutorial we're going to be covering those, and once we have all the variables, we can begin putting this quantum mechanical model together. And I just want to say this, guys, if you stuck with me and you're still listening to this video, probably this tutorial and the next tutorial are the 2 most complicated tutorials for a while. The quantum mechanical model is kind of new in chemistry relative to everything else, so it's kind of confusing subject, but once we get past this, then everything's going to start coming together and you're going to understand chemistry so much easier. So anyways, just stick with me for this tutorial, the next tutorial, and maybe the next one, and then it's going to be a breeze, I promise you. So anyways, thank you guys for watching. Don't forget to subscribe, and I will see you guys in the next tutorial.
Quantum mechanics and the shape of atoms as discovered by Schrödinger. We all know about quantum mechanics, which is of course the physics theory that describes atoms and elementary particles, how they move around like slushy little waves, and interestingly, it predicts what they look like, what shape they have. It was invented in the first couple of decades of the 20th century by a lot of people all working together. Amongst them were Planck, Heisenberg, Bohr, Davison, du Broglie, Einstein, and of course Schrödinger. These guys already knew a lot about atoms from the scientists who came before them. For instance, they knew that there are about 100 different atoms in nature, and that these atoms join in larger structures such as molecules, metal lattices, and salt lattices to make everything we see around us. But what they didn't know, what exactly was going on the inside of the atom, what it was made of, what shape it has. So they were doing experiments on that. And pretty soon they found out that atoms themselves are composed of smaller particles. They found the proton and the electron, and they were featherizing the neutron. And with the protons and neutrons, they almost immediately knew what the deal was. They realized that they were clumped in a very tiny core at the center of the atom. And that core was really small. A typical atom is about 300 picometers across, whereas that core is typically 0.01 picometers. So this leaves this big open space in an atom, and they realized that this open space was going to be the domain of the electron. But what they didn't know was exactly how the electrons are filling this space, if they are spinning around or orbiting or what. So they made an initial sketch. They called it the planetary model of the atom, basically the core at the center and the electrons spinning around in big orbits. It was their first idea of what an atom looks like. It proved to be incorrect, but it was a fine enough starting point. It made some very nice predictions, and it allowed them to start doing experiments, and they did. One man who was looking at these experiments was a Frenchman called du Broglie, and he was noticing something very interesting. He found that when electrons were forced to interact with matter, either through some physical process or by hitting a detector, that the electrons presented themselves as particles, as hard little balls of matter, kind of what you expect them to do. But when the electrons were allowed to move on their own, either by being shot through a crystal or allowed to wander through a vacuum, they always propagated as if they were waves. It was almost as if when you stop messing around with the electron, it would suddenly fall apart into some sort of wave function, some sort of probability wave that sloshed around all of space and predicted where the electron was likely next to be found. This was the first time they encountered particle-wave duality in matter, and it spelled disaster for their planetary model. Because this model really assumed that the electron stays a particle during the entire orbit and doesn't fall apart into a wave halfway through. So they needed a new model, but they realized that this model couldn't come from classical mechanics, because classical mechanics makes the same assumption, that particles stay particles. In fact, they would need entire new mechanics, some new theory that included the wave-like nature of particles. And this is when Schrödinger entered the picture. He had looked at the experiments as well, and he found one common theme running through all of them. In his insight, he saw one law of nature, one equation that seemed to hold no matter what you did. He called it the wave equation. Nowadays, we simply know it as the Schrödinger equation because it was the rock-solid core onto which all of quantum mechanics was built. Schrödinger realized that with this equation he was now in a very interesting position. What he could do is take an atom, any atom, take its properties, stuff like its mass and its charge, all those numbers, put that in that equation, do the math on it, and what he would end up with would be a series of pictures that showed what that atom looks like. He went on and did it for hydrogen, which is the easiest atom, it's just one proton, one electron. And that one proved to be crucial into unlocking the shapes of all the other atoms. And when he had worked his way through the math, these are the pictures he found. Ladies and gentlemen, the shapes of hydrogen. So this then is how an electron fills the empty space in an atom, not by spinning around, but instead with its blobby shaped wave function, which we call the orbital. What I've drawn here each time is just the same hydrogen atom with a proton at the center, and the electron has been allowed to go into a different orbital each time by giving it energy, for instance. And if you look at this one, these three blobs together form that one orbital. They house that one single electron. And this one makes a fine example. We can look a bit at its properties. What you can do in an experiment is take a hydrogen atom and prepare it in this orbital by giving it some energy, for instance. And if you leave it undisturbed, then the electron takes this shape. It becomes this wave function, this blobby shape. And if you then were to take a measurement of the electron, find out where it actually is, what would happen is this wave function suddenly collapses. It condenses into a single point, which we call the electron. If you then were to re-prepare your hydrogen atom in the same orbital, maybe give it some new energy, then you can do a new measurement, and you can find that electron in the same blob, or in any of the other blobs. And if you were to repeat this thousands of times, you would end up with a picture very much like this. Notice that there's a higher probability of encountering the electron at the center of a blob. There the probability wave function becomes more dense. But there's something interesting about these pictures, of course, something that is, well, staring us in the face. The fact that these blobs are not connected. There's an area in between where you cannot encounter the electron. So it kind of begs the question, how on earth is the electron traveling from one blob to another? Is it teleporting or what? This was one of the important questions that led to 40 years of heated debate that ended up with Einstein saying very angry things about dyes. But who cares? Schrödinger had made an important discovery. He had found the shapes of hydrogen. And using that as a basis, those that came after him were able to find the shapes of all the other atoms. They are very much based on hydrogen. They use the same orbitals. It's just that the higher atoms consist of more electrons, therefore they require more orbitals to house all of them. So you end up with a situation where the orbitals all get stacked on top of one another, overlapping but not mixing. They do, however, repel, because that's what electrons do, they repel one another. So the orbitals begin distorting each other according to some very complicated math. But these guys were also good at what they were doing. And, combined with Schrödinger's discovery, they had now made a link between physics and chemistry. A link which in fact led to an entire revolution in both of them. So with that, I would like to conclude by just saying, Mr. Schrödinger, thank you very much.
Video about energy levels, sublevels, and orbitals, all parts of the atom, and about how electrons are involved in these parts and where we can locate them. So the whole point of this video is, this chapter focuses on electrons. Where are the electrons in an atom? That's what we're going to get at in this video and start. So let's first refresh our memory and take a look at hydrogen. So if you remember, hydrogen has an atomic number of 1, and let's just remember from first semester that the atomic number is the number of protons, and if the atom is neutral, then we know our protons are equal to our electrons. That's what a neutral atom is. There's no leftover charge. So if hydrogen has 1 proton, then it has 1 electron, and we'll assume it's neutral. So it's this 1 electron. That's what we want to focus on. Where in the atom is this 1 electron? And that's what the point of the video is. So I have drawn a hydrogen atom for you, and hydrogen has 1 energy level. We'll learn later on in this video how to figure out how many energy levels. We can also call this energy level a shell. So this is the first energy level. It's the closest to the nucleus. It's also called ground state. The first energy level, and only the first, is the exception. It can hold up to 2 electrons, meaning it can hold less than that, but no more than 2. Every other energy level from there on out can hold up to 8. So if my hydrogen only has 1 electron, then let's go ahead and fill this in. Here's the 1 electron. Okay. I'm going to use little dots to represent electrons. So for the sake of argument, we're going to put an electron either here, 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 here. We'll kind of see there's a little bit of a pattern that I use. So I'll put the first one up there. All right? Okay, let's take a look at another atom. How about carbon? Well, carbon has an atomic number of 6 on the periodic table. Again, we know that's the number of protons, and if carbon's neutral, those protons equal the electrons. And so we'll assume it's neutral, therefore 6 protons means 6 electrons. Again, our focus are the electrons. How do we fill the electrons in an atom? So, like we learned last example, the first energy level, or energy shell, or just we can even call it a shell, can only hold up to 2 electrons. So, 1, 2. Top and bottom. Can it hold any more? No. Well, we said that there are 6 electrons. We just got rid of 2 of them, so there's 4 more left. The second energy level and all the energy levels from there on out can hold up to 8, no more than 8. It can hold less, but no more than 8. Again, we had 6 and we used up 2, which means there are 4 electrons left. So let's fill those in. 1, 2, notice my pattern, 3, 4. Again, total of 1, 2, 3, 4, 5, 6. So again, first energy level holding 2. The second energy can hold up to 8, but it's holding 6. Okay, that's great. Let's look at another example. Sodium. Sodium has an atomic number of 11, so we know it has 11 protons and 11 electrons if it's neutral, and we'll assume it is. Sodium has 1, 2, 3 energy levels. Again, you'll learn about the energy levels in a second. So I have 11 protons. Remember the rule. The first energy level can only hold up to 2. So there's 1, 2. The second one can hold up to 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay? All right, so that makes 10, right? 8 and 2 makes 10, and I have 1 more electron. These are my total electrons. So I need to use an extra energy level to get that to now 11 electrons. So if you count up all the black dots, a total of 11 electrons. Just a reminder, where are my valence electrons? Remember, the outermost energy level is where I found my valence electrons, and there's only 1 valence electron here on sodium. Okay, how about hydrogen's valence electrons? 1 valence electron in hydrogen. That's why they're in the same column. How about carbon? Ooh, outermost energy level, 1, 2, 3, 4. That's why carbon is in column 4 on the periodic table. Just a refresher. Okay, so now that we've seen how these electrons are filling in, let's go back to some of our terminology and refresh our memory. An energy level, as we just saw, has a sublevel within it, and within the sublevel there's an orbital. And again, I like to use this analogy, hopefully this is looking familiar, that an energy level represents the floors in a hotel. The sublevel represents rooms, and the orbitals represent the beds in the room. And remember, this is how we actually can find, or where we can find, electrons. So electrons are actually kind of like sleeping in the beds that are found in the room that are on the floor of a hotel. So kind of like, where can we find you? You are in a bed that is found in a room in the hotel floor. So let's take this analogy just one step further and look at this. Okay, so this represents a piece of the pie, and if we think of an atom being a circle, and then I've just kind of cut out a piece of the circle, okay? And if you notice here, I have energy level 1, N is equal to energy level 2, 3, and 4. 1 is the smallest ring, and so it's very, very, very small. There's not a lot of room. The only sublevel that there is in energy level 1 is sublevel S. In energy level 2, there's sublevel S and sublevel P. In energy level 3, there's sublevel S, P, and D. And in energy level 4, there's sublevel S, P, D, and F. So now you know the names of our sublevels. They're actually just letters. Okay? All right. Now, in sublevel S, there's only one orbital. Sublevel S, one orbital. Sublevel S, one orbital. Sublevel S, one orbital. In sublevel P, there are 3 orbitals. Wow, that's a lot. 3 orbitals in P, 3 orbitals in P. In sublevel D, there's 5 orbitals. 5. And in sublevel F, which you notice doesn't happen often, there are 7 orbitals. Now to help remind you about this, or help give you an analogy, here's the hotel that's back. You go to the first floor, which is our energy level, and you go to the room S, which is a sublevel, and you open that door, and there's one bed. 2 electrons can fit in one orbital, one bed. Now I go onto the second floor, and the second floor is even bigger, and there's more room. So I have room S and room P. In room S, always there's going to be one bed, so 2 electrons can fill in there. And in room P, there's always going to be 3 beds. So I got 2, 4, 6 total electrons can fit in there. Okay, and I go to the third floor. There's even more room on the third floor. There's room for room S, room P, and room D. Remember, room S always has 1 orbital. P always has 3, and now we see D always has 5. Look how many more electrons can fit in. Remember, each bed, or orbital, can hold up to 2 electrons. Now let's look up here on the 4th level. I have S, P, D, and F. We said S holds 1 bed, P holds 3, and D holds 5, and now F holds 7. So 2 electrons can fit here, 6, right? 2, 4, 6, 8, 10, and 14 electrons can be held in the F. And it keeps going on, but for our analogy right now, this is good enough. Okay? All right. So with that being said, there's actually a way you can arrange the periodic table, or the periodic table is already arranged, that can help you out with our sublevels. This is really good to sketch down. This section of the periodic table, the first 2 columns, are the S sublevels. The middle transitional metals happen to be the D, and the elements to the right, which are mostly nonmetals, but some of the metals, are the P. We call these the SDP block. Down below, the actinides and lanthanides are the F.
Professor Dave here. Let's learn about quantum numbers.
He knows a lot about the science stuff. Professor Dave explains.
Now that we understand that electrons are both particles and waves, we are ready to learn about how electrons are arranged in an atom. The location and energy of every electron in an atom is determined by a set of 4 quantum numbers that describe different atomic orbitals. An orbital is a region of probability where an electron can be found. There are S, D, P, and F orbitals with different shapes, and they look like this. Remember, these shapes are not electrons, just regions in space where electrons can be, and each one can hold up to 2 electrons. The more electrons an atom has, the more of these orbitals it will need to accommodate them all. The first quantum number is the principal quantum number n, which can have any positive integer value. We saw this when we learned about the Bohr model. It represents the energy level of the electron. Each orbital will have an n value, and the larger the value of n, the further away from the nucleus it is. The next quantum number is the angular momentum quantum number, L. This can have any value from 0 to n-1. For example, if an electron has an n value of 3, it can have an L value of either 0, 1, or 2, because 2 is 3 minus 1. The L value describes the shape of the orbital. When L equals 0, we are describing s orbitals, which are spherical, just one of these per energy level. When L equals 1, we are describing p orbitals, which are lobes that extend outwards on 3 axes. There are 3 of these per energy level. When L equals 2, we are describing d orbitals, which are weird looking, 5 of these per energy level. And when L equals 3, we get f orbitals, which are even weirder looking, 7 per energy level. Next, we have the magnetic quantum number, m sub L. This can have a value of anywhere from negative L to L. So if L is 2,
m sub L can be -2, -1, 0, 1, or 2. This quantum number determines how many orbitals there are of a type per energy level, and therefore describes a specific orbital amongst a particular set. When L is 0, m sub L must also be 0, and that's why there's only one s orbital per energy level. When L is 1, m sub L can have 3 values, which is why there are 3 p orbitals per energy level. An L value of 2 gives us 5 values for m sub L and 5 d orbitals, and an L value of 3 gives us the 7 f orbitals. The last quantum number is an easy one. It's the spin quantum number, m sub s. This one will be either 1/2 or -1/2, no matter what. So every electron in an atom has a unique set of quantum numbers. No two electrons in an atom can have precisely the same 4 quantum numbers, as is stated by the Pauli exclusion principle. This is because any orbital can only hold up to 2 electrons, and even the 2 electrons in the same exact orbital will have opposite spin values. So let's try to describe different sets of quantum numbers and what they mean. When n equals 1, L must be 0, and m sub L must also be 0. That means we are describing the 1s orbital. It can accommodate 2 electrons, which will have spins of half and -1/2, respectively. This is the lowest energy orbital, so any atom on the periodic table will fill this orbital first. The electrons in hydrogen and helium occupy this orbital since they have only 1 and 2 electrons, respectively. When n equals 2, L could be 0, which would give us the 2s orbital, or L could be 1, meaning m sub L could be -1, 0, or 1, giving us the 2p orbitals. The outermost electrons in the second row of the periodic table will occupy these orbitals. When n equals 3, L could be 0, giving us the 3s orbital. L could be 1, giving us the 3p orbitals, or L could be 2, giving us the 3d orbitals. A large atom will have to use all of these orbitals and more to house all of its electrons. The Aufbau principle tells us the order in which an atom will fill up its orbitals. This is determined by their relative energies. Orbitals that are further away from the nucleus have higher potential energy, so it'll be 1s first, then 2s, then 2p, 3s, 3p, and so forth. We can use this to determine the electron configuration of any atom. For example, a neutral chlorine atom has 17 electrons. So looking at the orbitals, each of which can hold 2 electrons, let's fill them up starting at the lowest energy and then climb upwards. The 1s orbital gets 2 electrons, one spin up, the other spin down. Then the 2s, then the 2p's, then the 3s, and the last 5 will go in these 3p orbitals. Hund's rule says that for electrons of the same energy, you put 1 electron in each orbital first before doubling them up. So 1, 2, 3, 4, and 5 gives us a total of 17 electrons for chlorine. That means chlorine has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. The numbers before the letters are the n value for the orbital. The numbers after the letters tell you how many electrons sit in each type of orbital. If you want a quicker way to determine electron configurations, just know which areas of the periodic table correspond to which types of orbitals. This area is called the s block. This is the p block. Here's the d block, and then the f block. When we are determining the electron configuration for an atom of a given element, the easiest way to do it is just travel left to right and up to down on the table until you get to the element, since each element has one more electron than the last. Looking at chlorine again, the top row is just the 1s orbital. That's full, so 1s2. Going to the second row, where n equals 2, we fill the 2s orbital, which holds 2 electrons, hence 2 elements. The 2p orbitals, which hold 6, so we pass 6 elements. Then the next row down, we fill the 3s orbital. And lastly, we get to the 3p's and count 1, 2, 3, 4, 5. 3p5. A common abbreviation is to use the noble gas from the row above and list it in brackets. This would be read as neon core, and it implies the ground state electron configuration of neon. Then you just list the valence electrons of the element, or the ones that correspond to the row it is in. We can use orbital diagrams to visually depict how the orbitals are filled, and they look like this. Don't forget Hund's rule, fill each set halfway before doubling up. For a quick definition, Atoms with unpaired electrons in their orbital diagrams are called paramagnetic and are attracted by a magnetic field. Atoms with all of their electrons paired are diamagnetic and are not affected by a magnetic field. So to summarize, N tells us the energy level, L tells us what type of orbital, M sub L tells us which specific orbital amongst a set, and M sub S tells us the spin. Each electron in an atom has a unique set of quantum numbers, and an atom will fill up orbitals with electrons according to the Aufbau principle until all of its electrons have a place to stay. This is a tricky concept, so if you feel confused, try watching one more time from the top. Otherwise, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Electronic configuration of atoms. We know that atomic orbitals are the substationary states, or the regions in space where the electrons revolve around the nucleus in an atom. The electronic configuration of atoms is a representation of the occupation of electrons in the orbitals. In other words, the electronic configuration of an atom specifies the order in which electrons fill up the orbitals in the periodic table. The order in which these electrons are filled into the atomic orbitals are controlled by three crucial guidelines or principles, which include the Aufbau or building up principle, Hund's rule, and Pauli's exclusion principle. Let's start with understanding the Aufbau principle. According to this principle, an electron always occupies the lowest energy orbital first before filling the higher level. For example, an electron always occupies 2s, the lower energy orbital, first, instead of the higher 3s orbital. The Aufbau, or building up principle, can be explained with the example of the hydrogen atom. Hydrogen has one electron. This electron enters the 1s orbital, which has the lowest energy. In other words, the building up principle states that the incoming electrons go to an orbital which has the least n plus L value. However, the orbital having lower n value will be occupied first, in case any two orbitals have the same n plus L value. Consider the example of silicon, whose atomic number is 14. 12 electrons can be accommodated in 1s, 2s, 2p, and 3s orbitals. Now, the last two electrons can enter into the 3p or 4s orbital. The n plus L values of these orbitals are the same. That is to say, 3p orbital has n plus L value of 3 plus 1 is equal to 4, and 4s has an n plus L value of 4 plus 0 is equal to 4. This means that both the orbitals have the same n plus L value, but the 3p orbital has an n value that is 3, which is less than the n value of 4s, which is 4. Therefore, the 13th and 14th electrons occupy the 3p orbital first. This means that the electronic configuration of silicon is Ne 3s2 3p2. The superscript represents the number of electrons present in the corresponding orbital. The second important rule to determine the electronic configuration of an atom is Hund's rule. It says that electron pairing happens only after all the available degenerate orbitals are occupied by one electron each. Let's use an example to understand Hund's rule. Consider the element oxygen with Z equal to 8. It has 8 electrons. The first electron goes into the 1s orbital of the K shell. The second electron will be paired up with the first electron in the same 1s orbital. Similarly, the third and fourth electrons will occupy the 2s orbital of the L shell. The fifth electron goes into one of the three 2p orbitals of the L shell. Let that one be 2px. Since the three p orbitals, 2px, 2py, and 2pz, are degenerate, the sixth electron goes into 2py or 2pz, but not 2px. Let's say it goes into 2py. Since 2pz is a degenerate orbital, the seventh electron goes into 2pz instead of pairing up with the electron 2px or 2py. Now, since all three suborbitals have one electron each, the eighth electron can pair with any of the three electrons in 2px, 2py, and 2pz. So, the electronic configuration of oxygen can be written as 1s1, 2s2, 2px2, 2py1, 2pz1. The arrows indicate the electrons with a spin plus 1/2 and minus 1/2. Let's consider the nitrogen atom. It has 7 electrons. The first 6 electrons have the same arrangement as that of carbon, which is 1s1, 2s2, 2px1, 2py1. The 7th electron will enter only in 2pz, but cannot enter into 2px or 2py. This configuration is 1s1, 2s2, 2px1, 2py1, 2pz1. The third important rule for electronic configuration, that is, Pauli's exclusion principle, states that no two electrons will have the 4 quantum numbers the same. This means that two electrons can never have identical values of n, l, m, and s values. Because of this rule, a single orbital can have only.
We've already seen that the allowed values for the spin quantum number are positive 1/2 and negative 1/2. So an electron could have spin up or an electron could have spin down. And remember, spin is in quotation marks because we can't really visualize an electron spinning on its axis. That's not really what it's doing. And so we just call it the spin quantum number. And so let's say we have 2 electrons, and each of our electrons has spin up. So let me go ahead and draw that situation here. So we have 2 electrons with spin up. Well, an electron is a moving charge, right? Moving charges produce magnetic fields, and so an electron is really just a tiny magnet. And when you have 2 electrons with parallel spins, the magnetic fields of those electrons add together. So we call this situation paramagnetic. So this situation here is paramagnetic. The magnetic fields of the electrons add together. If you have a situation where you have 1 electron with spin up and 1 electron with spin down, the magnetic fields of those electrons cancel each other out. And so we call this situation diamagnetic. And let's get some better definitions for paramagnetic and diamagnetic. So let's move down to here and let's look at the definition for paramagnetic. So something that's paramagnetic has 1 or more unpaired electrons. So we talked about an example where we had 2 unpaired electrons. But of course, you could just have 1 unpaired electron, right? So that's like a tiny magnet with its own magnetic field. And so something that's paramagnetic is pulled into an external magnetic field. It's attracted to an external magnetic field. And we can figure out if a sample is paramagnetic or not by using this special balance that I have. I have this picture of this balance drawn down here. So let's say that our paramagnetic sample is in here, so right there in magenta. And we haven't turned on the magnet yet. So here we have a magnet. There's a north pole and a south pole. So before we turn the magnet on, let's just say that our paramagnetic sample is balanced by some balancing weight over here on the right side. Right? So there's a pivot point right here, but we have everything balanced perfectly. Right? So let's now turn the magnet on. So we turn the magnet on, and the magnetic field lines go from north pole to the south pole, like that. And if we have a paramagnetic sample, right, with 1 or more unpaired electrons, our paramagnetic sample is pulled into this external magnetic field that we've just turned on. And so this is pulled down, right? So this whole part is pulled down. And so let me go ahead and redraw it here. So this would be pulled down into the magnetic field. And so our paramagnetic sample, right, is pulled into the magnetic field. All right, what does that do to our balance? Well, of course, that's going to pull this side down, right? And so that's going to pull, and our balance is going to rotate about this axis, right? And so this part's going to go up. Right, so just simple physics, and so this weight's going to go up, and so it's like our paramagnetic sample has gained weight, and of course it hasn't gained weight, it's just experiencing a force. There's a magnetic force because it is a paramagnetic substance, and so this balance allows us to figure out if something is paramagnetic or not. Let's look at the definition for diamagnetic. So for diamagnetic, all electrons are paired. Right? So if we have spin up, we have spin down, and so the magnetic fields cancel. And so a diamagnetic sample would not be attracted to an external magnetic field. Actually, it produces its own magnetic field in the opposite direction, so it's actually weakly repelled by an external magnetic field. So we have these two definitions, paramagnetic and diamagnetic, and we can figure out if atoms or ions are paramagnetic or diamagnetic by writing electron configurations. So let's look at a shortened version of the periodic table, and let's look at some elements, and let's figure out whether those elements are para or diamagnetic. Let's start with helium. So helium right here, we need to write the electron configuration for helium. So this would be 1s1, and then we get 1s2. So I'm assuming you already know how to write your electron configuration. So we have 1s2, which means we have 2 electrons in a 1s orbital. So here's our 1s orbital. We have 2 electrons, and they must be spin paired. Right? So the electrons are completely paired, and that means that helium is diamagnetic. So helium is diamagnetic. So helium atoms, I should say. Let's do carbon next. So let's find carbon. Let me change colors here. So here's carbon on the periodic table. If I wanted to write an electron configuration for carbon, well, it would be 1s2. Right? So I'll start 1s2, and then we have 2s2. So 2s2, and then we have, we're in the 2p1 and then 2p2. So 1s2, 2s2, 2p2 is the electron configuration for carbon. If we write an orbital notation, right, so we would have our 1s orbital here, and our 2s orbital here, and then we have 3 2p orbitals like that. So put in your electrons. We have 6 electrons, right? So 2 in the 1s orbital, so we put those in. 2 in the 2s orbital, we put those in. And remember Hund's rule, right? We have 2 electrons in the p orbitals, but we don't pair those spins, right? We don't pair those spins. And so we have unpaired electrons, right? So we have unpaired electrons here for carbon when we draw out the orbital notation. And unpaired electrons means that carbon is paramagnetic. So carbon is paramagnetic, carbon atoms anyway. All right, let's do sodium next. So let's find sodium down here. So here's sodium. We need to write the electron configuration. All right, so that would be 1s2. So let's write 1s2 in here. 2s2. Then we have 2p6. So 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So 2p6. That takes us to the 3s orbital, right? And so 1 electron in the 3s orbital, so 3s1. So 1s2, 2s2, 2p6, 3s1 is the electron configuration for sodium. If we did that on our on an orbital notation, right, we would have 1s orbital. Right, so we have 2 electrons in the 1s orbital. 2s orbital, we have 2 electrons in the 2s orbital. 2p orbitals. Right, we have 1, 2, 3, 4, 5, 6, and then we have 3s1, right? So we have the 3s orbital right here, 1 electron in the 3s orbital. Well, notice, right, 1 unpaired electron. An unpaired electron means paramagnetic. So sodium is paramagnetic, sodium atom anyway. All right, finally let's do sodium ion, so Na+. So the sodium atom has equal numbers of protons and electrons, but the sodium ion, we've lost one of those electrons. Right? So we're going to lose this outer electron here. Right? So the sodium ion has this for an electron configuration, 1s2, 2s2, 2p6. And so we lose this one electron. Notice for the ion, now we have all paired electrons. Right? So everything here is paired. And if you have all paired electrons, we're talking about diamagnetic. So while the sodium atom is paramagnetic, The sodium, I misspelled that there, the sodium ion is diamagnetic. And so it's just about writing your electron configurations and thinking about the definitions for paramagnetic and diamagnetic.